Hey guys, how's it going? Welcome to another episode of Ferris Makes Hardware. This is episode 30. I like those nice round numbers. And again, my green screen's kind of messed up. Again, it's really hard to predict the lighting in this room in the summer. And we're just going to have to live with that for now. Whatever. So this is kind of an exciting episode. As you guys know, I haven't been streaming as much lately. But last week, I decided to just you know what? I kind of want to work on this Rasterizer again. So we started looking into fixed point division for the perspective correction stuff that we're doing. Mad Moose says it's only round in base 10. Very true. I don't know what else to say to that, but yes, definitely. Anyway, we started looking at fixed point division for the perspective correction in the Rasterizer. And again, this is only the software model that we were talking about, and made some progress, but of course the thing didn't quite work, didn't really seem to have enough precision. I looked up with those kind of division algorithms that we were using, and typically you need to actually round the inputs or normalize them beforehand, which is not something we were doing in the testing. So that explains, I think, why it wasn't able to quite work as we expected, which is fine. Of course, yesterday it occurred to me that we can just do a lookup table, and that's probably enough precision for the particular divide that we're doing there. So I may end up doing that. In particular, it's a reciprocal, so I might end up just using a lookup table. However, earlier this week, I think it was on Tuesday, I had some time, and I was like, instead of sitting there massaging the rasterizer the whole time, I kind of want to do something a little more exciting. I find it's helpful to kind of come up with ways to make presumably, or I guess the word is ostensibly, a lot of progress in a short period of time, such that it feels really motivating to continue. And right now it's kind of boring, kind of massaging the renderer until it's all ready to be implemented in RTL. I thought, well, why don't I just actually strip that down to its bare minimum and start implementing that in RTL? And I think that's actually useful for a couple reasons. One, I was going to do that anyway. Why not start now? And two, I actually think it's helpful because I need to get a better idea of how the RTL will look. I understand roughly how the pipeline's going to look, but there's parts of it that I would like to be a bit more concrete. So yeah, why not start that now? So I actually made some progress with that, and I'll show you guys what I did. I need to clean up my workspace here. Let's see. I've got all kinds of windows over here. Oh yeah, here, by the way. This says, assuming ND has been scaled so that 0 is less than D is less than 1. I don't think we did that. So you need to do that for the first part. But yeah, anyway. Let's actually close all of this. And I'll bump up the font size a bit. So let's see. Actually, this is in that trim project. All of this is, isn't it? Yeah, all this is. And then a little bit of Kaze stuff, which I'll have to get to. Oops. Oh, come on. This week on Ferris, can't remember how to use this editor. Okay, so if I go into, let's close some of this stuff. Gloat. So this is the Rasterizer with an OpenGL front end thing that I was working on previously. And so this is kind of the most complete Rasterizer model that I have. It has quite a lot of fixed point stuff, and in particular, here is that divide that we need to replace, which again, I think a lookup table is probably going to be enough, which should be a lot faster and simpler. So this might be easier than I expected, but that occurred to me after I started this other stuff. So anyway, this is still in Rust. That's kind of a key point, but it is mostly sort of isolated. But I decided I was going to strip that down to its bare minimum. So what I have here is another version of this. I made a new little Rust project called Trim, and I haven't pushed this anywhere. This is just a little experiment. So I took the same rasterizer from this more complete model, and I just stripped it way down. So all it has is some counters for the 3 edge functions for the triangle, and then a color. And I think it also has an internal color buffer. Yeah, exactly. And then this rasterize primitive function. So the idea is that you would set all of these up and then call rasterize primitive, and it will go over the entire tile and rasterize the triangle into this color buffer. That's it. It's not a lot of code at all because this kind of algorithm is really simple, but yeah. Also, it's quite slow because, sorry, just closing windows. Closing lots of windows. It's bugging me. But yeah. Also, it's a bit slow because this is doing everything serially. But of course, on the hardware, we pipeline all of this, or at least that's the plan. So we should be able to output, when this pipeline's saturated, it'll be outputting a pixel per cycle. And in fact, I might end up being able to have multiple of these in parallel, because I think we can, with the DDR controller that we have, well, it won't be driven by that anyway. I don't know. We'll see. But the point is we can sync like 128 bits per cycle. And I think we can match that with the pixel pipes if we have 4 of those in parallel, for example. But anyway, let's see. Yeah, so I made this little model, right? And then I bootstrapped it. And this, what you'll see here, is actually one step ahead of where I'm talking about, but I'll get to what this actually is. So what I did is I just bootstrapped it with this top-level code that I can just show you here. That creates a mini FB window, and then it draws 5 triangles per frame, like as fast as it can. And so it makes some random vertices. In this case, vertices only have positions, just with what I'm doing here. And then creates a random color with full alpha. And then that's basically it. Then it calls this rasterize triangle. And this rasterize triangle thing will do what I mentioned. It'll figure out all of the edge function stuff. And then it goes and it sets up all these registers, and then eventually calls rasterize primitive. Yeah, it loads everything from the main buffer into the tile buffer, and then calls rasterize primitive, and then it reads stuff back from the tile buffer back into the back buffer. Now, normally this loading stuff, you'd normally collect all the tiles and make a triangle list per tile, and then you would only move this stuff to and from the buffer like once per draw call. But in this case, I'm doing it once per primitive because I'm lazy, at least for now. So that looks like this, right? And then I took it one step further, and you'll notice that this doesn't actually interact with this struct here. In fact, I believe it's including that is commented out, right? The module definition for that. So what's actually happening here is I added a build script for this little project that includes Kaze, my HDL, and this creates a module called color thrust, right? So this is an actual RTL implementation of the same thing. Now it's a bit different because like it's still, we've got all these registers, so we can kind of compare the two. All these fields here become registers, and it's a little more complicated already because I've also exposed like a write port and a read port to read and write these registers. Actually, did I do a read port? I think I did, but I think I only actually ever output this busy signal for now out of laziness. So it's a bit more complicated because we have to create the register, and then we have to create the logic to drive its next value, which is normally like we need to check the write and that we're writing to the right address. But then otherwise it'll retain its old value. So not terribly complex logic, but I repeated a bunch of times, again, out of laziness, which we're going to end up refactoring this later. But I don't know if we'll do that today because there's some other stuff I want to do first. But anyway, it's all the same values, same with like color. And then there's also the color buffer, which is this internal buffer, and that's an internal memory where we have 32-bit entries and then as many pixels as there are in the tile, which I think is 256 pixels, so that many entries. And then we also drive the write port of that basically with this logic. So it's basically the same, like it's the same logic, but it's kind of all inverted, as if you had done this in like a functional style. Instead of this more imperative style, which makes it a little bit more complicated, but not that much really. So it's a bit more code. And of course my HDL isn't the least verbose thing in the world. But anyway, it ends up working, right? So what you're actually seeing here is, is the RTL, because in this build script, we generate this modules file. So if we go into release, whoops, let me open that again. Release, build, one of these builds. I don't know, probably this last one, but I have no idea if this is up-to-date one. And you open this modules. This came out of my compiler. So this is the Rust simulator version of this. And again, you have all these same register values, but you also have these next values, which represents what they're going to be on the next cycle. And then here's all that stuff for that one color buffer memory and its read and write port. And then, of course, there's a reset way to tick the clock, which updates all the registers and the memory contents if the write ports are driven, and then are driven high, and then propagating all the signals through the whole thing. And so then in main here, you'll notice I made a new color thrust struct. By the way, color thrust is the name of the rasterizer, which I just think is an awesome name. It's kind of ridiculous, but that's what's cool about it. Here I've added functions to, for example, read a register, write a register, or write the color buffer, read the color buffer. And you can see what that does here. So for example, if we want to write a register, I think this is a simple case. We give it an address, which is an offset, like a register number, and then the data we want to write there. And this will, on this generated struct here, I'll open that again so you can see. Whoops. No, that is the one I wanted. Here we go. So it will drive the register write adder and register write data inputs here. And then, yeah, also drive the reg write enable high. And then it will propagate the signals throughout the design after it has changed those. And then it ticks the clock, which should mean that the write is asserted. And then we're on the next clock. And so then what it does is it asserts that reg write is false, then also propagates the signals again. And that's actually the only time I tick the clock in this, right? And then, well, there, of course, I do that also for like reading registers, but then I also have these similar ones because I added a separate port for reading and writing the color buffer. And this may not be the final interface for the actual rasterizer, but this was a simple interface that I could bootstrap relatively easily. So that's what we have so far. And then the last thing I did is I also added this rasterize primitive function. And in this case, you can see it uses the same write reg function to write this reg start adder register. So if I go back to the build, I have these consts. Oh no, that's in color thrust defs. That's what this is. Yeah, here it is. So you can see some things about like the tile size, and then all these definitions for where the registers are. Actually, see that's hidden by my overlays a bit, but looks like that. And then, yeah, so it writes the start address, which is going to kick off the rasterizer by writing a 1 to there. And then you can see here, it's then going to read the status address, the status register in a loop until that's 0. And because read register ticks the clock, that's what's actually driving the simulation. So the cool part about this is that the top level code looks like identical to what it did before, except that like instead of setting those values on the struct, it calls like write register, which is semantically what we're doing anyway. So you can see here the bootstrapping will figure out all the edge functions, and then in this case it actually creates the color thrust instance, but eventually I want to remove this. But then like here it figures out these edge functions, so it uses write reg to actually write all those. And my syntax highlighting is all messed up. I guess we'll ignore that. And then it will do some more at the end here for the min values, and then the color value, and then finally it calls rasterize primitive, which again will do that write to the start register and then loop on the status register. And then it works, right? Like this is drawing a bunch of triangles, which is really sick. So that's absolutely excellent. Like I'm really happy about that. So the next step, like this is a basic rasterizer. Of course, it's missing a lot of features compared to the other model that I have. Like it's missing all the texture mapping. It's missing depth testing. It's missing any kind of interpolation or blending or any of that stuff. But that's fine, right? This is where we have to start anyway. So what I think I want to do next is this is still running in sim. I want to get this exact same test running, but I want to actually get it running on the FPGA. And that's that's my, I guess, stretch goal for today, because my goal is to really clean stuff up and kind of work towards that. Like, if I don't meet that, I'm not going to be disappointed. But that's kind of what I'm working towards today. And I want to do that before I start extending the implementation here, just for fun. I think that sounds cool. Now, the reason why I don't know if we'll actually be able to reach that goal today is basically I've got some other stuff that I think we need to do before I can reliably do that. First of all, this rasterizer, the way it's written right now, actually uses, it has a couple really big conditionals that affect a lot of signals. And I think Kaze right now in this conditional construct only supports up to 8 signals that it can modify at one time, or like tuples of size 8 that it can return. And I actually hacked my local build to handle more than that. And I actually might do a proper release with that. I'm not sure. But anyway, that means that the Kaze version that this is building against is actually different from the one that the main Xenowing project is built against. And if I just move this over, then it might not work. But maybe actually releasing a Kaze build, a new Kaze version that bumps up that size is fine. Or I'll just hack in my local build all of them to point to this build. Whatever. I'll probably just do that. In addition to that, we need to do some memory mapping in this RTL. And we need to, let's see, what else do we need to do? Yeah, in this top level stuff, there's this Xenowing blaster thing, which right now can communicate with the device. I want to maybe make this into a library, at least this part with the devices, and then make this like Rasterizer test use that library rather than always modifying this same top level code. And let's see what else. Or maybe I do just want to hack this top level code. Like, I don't really care if I make a bit of a mess here, because it's a useful goal. But then the last thing I need to do is I need a way to make these register reads and writes here. I want them to go over UART and actually interact with the FPGA itself. So what I think I'm going to do is still have these same kind of functions, but then have them be translated again to reads and writes on this other device. And so essentially what I want to do is I want to have the program that runs on the FPGA on the system. I want to have that, let's see, program source main. I want to have this have a loop that will interpret commands sent from the host. That's kind of the point. And so then I need to make a little command format that will represent some register reads and writes. And if all of that works, we should have this exact same test that we have here, where it's just drawing random triangles. We should have this running a lot slower because it's moving a lot of data over a pretty slow UART connection. So it'll be a bit slower, but it should run against the actual hardware, which is really exciting, at least to me. So I think it'll just work if we do all that stuff. But it's a bit of a long road. But that's the next kind of step that I want to take before making the Rasterizer more full-featured, even in Sim. And the nice thing about that is that our round-trip time for all this stuff shouldn't be that long, because since we have the whole Xenowing, at least in the form it is now, bootstrapped in Sim, we should be able to do that without ever touching the Xilinx tools or the FPGA compiler for quite some time. Kehost, is that how you say that? This is VS Code, I think. Visual Studio Code. So yeah, I guess I'll just get started with that then. Yeah, I think. I don't remember. It's whatever editor I found on this machine. Gorgeous Dong, thanks for the follow. Always feels good to be followed by a gorgeous Dong. Yeah, I'm really happy with VS Code. I do a lot of stuff over SSH at work, for example, and then it just kind of works. So I can have this like running on my local machine and then have a server running on the target machine and do everything over that, which is really good. And also it's pretty responsive. I used Sublime before this, and then finally made the switch to this for like everything. Plus it's cross-platform, which is really great. It's kind of the same experience everywhere. I need to have some cooler themes though. There's some guys at work that have way cooler themes than me. Yeah, the target machine can be Linux. I don't know what else it can be, but it can definitely be Linux. That's at least what we're doing, which is nice. And Sublime is great too. In fact, I think Sublime is still a bit faster than this, but this is good enough. So I think actually the thing that I want to do first is kind of go top down with this, and work on the program and getting it to do like memory reads and writes, because the only thing that I actually needed here was just reading and writing 32-bit values. Everything else works against that interface except this Rasterize primitive, but again, that is written in terms of reading and writing registers, so this code should end up being basically the same. But yeah, then I want to start with the actual program. So if I go back in here and I go back to Xenowing MISC XW Blaster, and this might be a really slow build. So here come the, oh no, it's already built. Great. I never get into Vim, but I did use Emacs for a while. But yeah, so this is the current Xenowing hardware running in Sim, and then the program running on that. And the nice thing about this is that I can change this program relatively easily. So I think I'm going to start with that. And we're just going to invent some stuff for a protocol here. I think, let's see. I want to go actually Blaster main. Put this over here. I might want to have some like consts for these values here, these commands. But for now, I'll probably just not and be lazy. So this program, this will run on the Xenowing again, and then this one over here is running on my host machine. Let's see. So I've got a lot of like random stuff going on here with like a frame buffer and it filling some stuff. And we don't need any of that actually. So I'm just going to get rid of it. In fact, all of this I'm going to get rid of. This I'll keep. It's very useful. Yeah, so the FPGA doesn't require it. The whole thing is that I don't have a Rust compiler set up for risc-v. So on the FPGA, I've implemented a risc-v CPU, which is using Verilog that comes out of my HDL. And that, of course, runs this processor. And then that's just going to execute risc-v code. And again, because I don't have a Rust compiler for that or any of that stuff set up, which is, I think is possible, but I haven't done it yet. It's just easier to bootstrap C on that. And so that's why this code that runs on the device is C. Yet the code that's running on my PC that it's communicating with over serial, that's Rust. Because I would prefer to do Rust everywhere, but in this case, it was easier to bootstrap C. It's probably not that hard to bootstrap Rust for risc-v anyway, but it looked more complicated than just using C, at least to start out with. And I also don't have a full C standard library running on this yet. I haven't bootstrapped that much. I just have been making what I need. So here I'm actually going to write something like, I don't know. Ready for commands like this. And I'm even going to be lazy here because I haven't tried this in a while. Actually, I'm gonna get 2 terminals. I think my makefile still doesn't cover the program RAM, so let's do that. I have to do make here separately, but then I think if I just do run here. Oh, I know what's happening. That's funny, actually. It's since this is returning this princess, and then it doesn't do anything, so I actually need to do like a while true. That's funny. Because that returns, then it returns to the boot ROM, which then returns, and then the boot ROM's entry. Yeah, it just jumps to the stub again and it restarts. That's funny. Okay, there you go. Now it's just ready for commands. So this is the nice part. Like I can change this, and actually, if this were running on the Xenowing itself, on the FPGA itself, I could also just iterate on the program like this. But then we're gonna eventually add the Rasterizer hardware, and then it's easier to recompile the simulator than it is to recompile the FPGA stuff, which takes a long time. I don't know if Rust has. I mean, it's been a couple years since I looked, to be honest. But I don't know if Rust has like officially supported targets for risc-v. I think you have to. I guess through Zargo you can probably get it. I don't know. We'll worry about that later. No, I haven't heard about that. Host. But it sounds cool. Captain Cheesecake, thanks for the follow. So let's do this. We might end up printing a lot. Actually, yeah, we don't want to print there. But what we'll do is this. We'll do XW. I think actually the boot ROM has code for this. Yeah, it just reads this. So if I did something like command, then we can do switch command. And here I'm just going to make something up, I guess, right? Whoops. That's not the right language. Here we'll do something like right reg. And so far we won't make this actually do anything, but we'll do something like Uint32T adder is 0. Then we can do adder. In fact, I think I have code to do this like this. I should actually just do like a read U32 thing here, but I'm being lazy for now. I was doing this for print that. Great. I'm going to do something like this. As you can see, I don't have printf, but that doesn't matter. I have these put s variants, which is good enough. I think I called this data in the other one. Oops, I did not rebuild this. What? What did I do here? Is it one of these things where I have to make a new scope for this? I think I do anyway, but... yeah, fine. There's a bad error message for that, but okay. Yeah, this is like ready for commands, but it's not sending it any. So let's see. Right now we can just go into this host code. So I guess I can first try to read something. This blocks on read, doesn't it? You know what I might do? I might actually send like a ready byte. Like I'm just inventing a crap protocol here. But just the way I've written this, I think it's going to be easier if I do something like this. Actually, I'm still going to do that. That way we can have something here. And then we can just do something like, I don't know. I did some of this crap too. I need to refactor a lot of this stuff, but I just don't care right now. So if you do something like fade babe and let data is dead beef, then we can write 0. Again, I need to do proper write things here, but this is one of those days where I just kind of feel like making a mess. And I want to do this too. Oops. That's exactly it, Aaron the German. So this didn't work. Oh, probably because I didn't rebuild this, I think, after I added that 02. There we go. So there, load the program, and now it's actually doing the writes here. Okay, so this command processor seems to work. You can see that the host got a request for command and it sent the command, and then you can see that the program on the Xenewing received a write reg command and it got the correct address and the correct data. Great. Let's see. Yeah, I need to do like write word and also read word. That'd be really nice. But at the same time, I'm sitting here thinking about flow control, and the sun's getting in my eyes. It's really annoying. I'm boiling in here, by the way. It's so hot. Let's see. I just got like a mad headache from the heat. Anyway, because I don't like this loop sits there and waits for commands from the device, and this loop sits there and also waits for commands from the host. So I probably have to refactor how this works. You know what I might do? I think I'm going to do this, actually. I'm going to break the loop here. Or not even that, actually. Well, no, because I actually still need to run this command processor thing. I got to figure this out. I'm glad I started somewhere. So I actually need to run this on the host because that's actually how this printing works, is that for every character, the Xenewing will send a 0 byte, this putc, and then it will send the byte of the character, which is really inefficient, but who cares, right? This is not important that that's inefficient. Of course, printing all of this stuff, by the way, is going to be real slow, but that's only for testing. Actually, you know what I'm going to do? Yeah, since I'm just hacking this anyway, and I actually don't need it to print while it's actually working on actually rasterizing stuff. Or maybe I'll just do like a frame here and then refactor this loop. Because the other thing is we need this loop to happen first, because this is also how it loads the program. The same program that is running here, there's a boot ROM that sends a 1 command, and then it expects that the host is going to go and read a file with a particular name, which I think is also determined here. And then that's actually what gets loaded, loads this program. I could also just have 2 different threads here if I wanted to, but I don't think that's a great idea. I'll probably just hack this. So say here we'll do like a I'm ready for a frame command, and then I can do this. And then I can have like a case 2 here. So that should be there. And then exit this loop. And since I don't want to use goto here, I'll do this. There we go. So Xenowing can send a command to do a frame, and then the host will just do everything that needs to do for that frame in this loop and assume that that's the only thing it's doing. And then eventually it will send a done command here back to the program. That's a good enough protocol. This is not great, but it's fine. This is as complicated as it needs to be. And it looks like it still works. We're gonna do as well like a read command. I like to have these in hex. I don't know why. Also, again, I'm sitting weird to keep the sun out of my eye. That's just how it is. So actually, yeah, this right. This will actually be right word, read word. And here we only expect the address. So right now I'm just doing this to test that we can set commands and that they're received, and then I'm going to remove the printing after. So let's do a bad idea. Like that. And then I also actually want, I do want this to return some data in a sec, but it won't work yet to do that because it's printing. But there you go. You can see that it receives the correct data, which is what we want. And in fact, since I haven't changed any of the ROM, this should actually work if I run this on the actual device. I think this will work. Look at that. That's running on the actual hardware. Because again, it loads the program from the host. We only change the program and then the host. We only change the program that runs on the device and the host. We haven't changed any of the hardware, so this actually works on the real FPGA, which is pretty sick. I'll turn that off and it will break. Great. That's awesome. That always feels good. I'm really glad I took the time to set all this up. And as you can see, it's slower in sim, which is expected. But the iteration time is faster, so that's why we're doing that. So now we actually want to make this useful. So instead of just printing all this stuff, we're going to do some writes. So let's say we'll do Uint32T data is 0x fade babe. So we're going to return that. And we can do data shift right 0 and XOF. Like that. So here we're going to do this. We're basically going to do this same thing here. But for these, this will be device.readByte as U32. And like that. And then we can line. Yeah, so it tries to write some data, it tries to read some data, and then we're going to expect to see fade babe. I'm not going to check that here. I'll just check it visually. Oops, I forgot to do that. Yeah, data return fade babe. So we are communicating. And again, I'm going to do the same thing on the actual hardware because it's just so cool to see it. It makes me so excited. Yep, that's working. Ready for commands. And the next thing I want to do, actually, this will be kind of cool. I didn't check the data that's returned. I actually want to do this. I actually want to look up the data. So if we say this is going to be a uint32t pointer like this, I think that's the correct precedence and everything. Then we should be able to read actual data. And so then we want to send this a real address. And we want to figure out what that is. Now I have in this doc a memory map. So if we wanted to, for example, we can read from boot ROM if we just do 0. I think that's probably a good idea. At least start out with. Again, we can change this. Let's try that. So again, we'll do it in sim first, just because that always feels smarter to me. And what we should see is a particular byte pattern. We see 2500006F. And if we go into this program here and we do risc-v ob none embed obj dump -d, and I actually think we need to do /boot ROM in here. There should be a boot rom.bin. Actually, we'll do the elf. That's good enough. But then the less. And we should see here at 00, we see 2500006F. So this actually works to read data now. And again, I'll do this on the actual hardware because that's just badass, right? And there it is, same data. Ha, that's so cool. Like, of course it works, but it's still exciting to see it. So let's do writing bytes now as well. So in this case, we'll do exactly the same thing. We'll get a pointer at adder is data. Let's get rid of this printing now. That should work. However, here now we should probably do like some actual address. So again, if we go back to our memory map, which is in here. I don't remember how I allocated this. looks like the stack RAM plus length of RAM. So the stack grows down from the top of RAM. I should actually make a proper like region for that in this map to make sure that well, I'll probably have to do that anyway to make sure that we eventually have a heap. But I haven't done that yet. So I don't want to just write the top of memory because that's going to fuck up our stack. Now I have 128K of this, and I think the program, I'm actually looking at the wrong linker script, which I think is fine. I think they end up being the same right now. Yeah, they are. So the program RAM is at this area. I guess we still execute out of that. I don't think it copies itself to text. If we look at entry, it copies the data sections. This should say from program RAM into, what did I call this? RAM. That should be DDR3. It's not yet. It's internal SRAM, but right now, but it will be DDR. So it looks like it copies the data sections and then clears the BSS sections. So actually, I think at the end of RAM, it's probably safe to do that. At the end of this region, it's probably safe to read and write. In fact, if we look at, if we do -X here, I don't know if that seems to be a bit much actually. -H, I think, gives us less. Yeah. And here's our address. So you can see BSS is actually here in the image, but then it's expected to be out here in actual RAM, which is what that initial code does, is copies all that stuff. Right, it copies the data first, and then it just clears BSS. So anything above this, I think, is fine. Because again, text is all within that program RAM area. And always that large. It's fairly small. Doesn't need to do much. But yeah, so if we wanted to test this again, blaze it. 1000 100000 should work. That's 64K. That's like at half of RAM. Would be a safe space, I think. So if the address was 0x1001, like this, U32, we can write dead beef in there, and then we give it the same address to read, and it should give us dead beef. That's the idea. I don't think I changed this, did I? I did? Don't remember doing that. Oh yeah, to actually make the writes do something. I guess this blaster thing doesn't need to be done in release. But there you see it's dead beef. And actually, well, I should have maybe read it before writing it. I'm going to do that. I'm going to swap these. And that way, it's kind of a cheeky way to test this, but I'm going to swap these and then write a different value here. Well, actually it doesn't matter because now we're running in sim, so everything gets reset, which probably I would have done anyway on the hardware. But the point is, we should see the first time it read, we got whatever, some undefined value, but I think it's always going to be 0 in this case. And then we got the actual data on subsequent reads. So that's sick. Now we're able to read and write memory. Gonna do it on the hardware again. Whoops. And again, here we should see basically the same thing. We had 0 the first time. I don't think I wrote the RTL to always assume this is 0 for the initial contents, but I think that's generally what you'll get if you end up getting one of these memory blocks in FPGA. I think they have some guaranteed internal contents. But that's great, right? This works. To be able to read and write memory. Okay. So now I want to get this rasterizer into the Xenowing hardware. And that is hopefully not going to take too much. So if we go into Xenowing RTL, this should be relatively straightforward. We're going to add in here, we're going to add color thrust. So pub mod color thrust. And I'm probably going to end up taking this like sim thing that I did for this and moving it into this sim folder and sort of keeping it as its own, or as its own project, or like its own like test harness, because that's really useful to be able to test it just with a little window like I've done here. But we'll do that in a bit. Right now we just want to take the trim color thrust, and I'll just copy all of this basically. No, this is the wrong one. That's not what we want. I did it in build. Is where I had this module def for now, which is fine. I need to change that though. So for example, like Buster here, we use Kaze and we have these generate functions. The kind of patterns I do for this, they're not like set in stone. It's just like I'm making this up as I go, but I'm still going to try and copy what I did here. So if I do file color thrust.rs, this will also use the HDL library. Yes. Actually, do I need an S? No, because we don't need to take the mod name here. Then there'll be C with this lifetime context. I think that's it. And then we're going to return a module reference. And here, this is where we do the color thrust stuff. So we'll do this. And I think I also call this M here normally, and then return M. I think that's what I've been doing. Yeah, FIFO does the same thing. Yeah, we don't need to do return in Rust. Just do M. And that should almost work, except these defs right now are here. And I think what I'm going to do is just put these here. This is what I want. Because then the top level code is gonna, the build script is gonna include, or the build dependencies are gonna have this RTL lib in order for it to generate this module. And in addition to that, the runtime top level code is also gonna have a dependency on this library, and then then it's going to be able to also include this module there and then get it all these definitions, which it needs in order to figure out like all these register offsets and stuff. That's cool. Status header. I guess I don't use this anywhere. But here, yeah, there's this one's down there. Or is it not? What's going on here? Yeah, whatever. This will not work because these conditionals, again, these tuples are too large. So I need to point all of this stuff at the other version of Kaze, which right now I'm going to do just like this. Oops. I think because this RTL, so then 1 up is going to be the Xenowing. So it actually needs to be 2 up like this. And then in the Xenowing blaster here, we're going to end up doing the same here. And then we're also going to have a dependency on this RTL library at runtime. or for the actual program, not just for build time. And that, again, will allow us to get it at those other constants. I'm just going to build this, which hopefully works. It didn't. Let's see. As a dependency of package Xenowing Blaster. And I think that's because these paths are not correct now. Because this is nested in this misc directory as well. Not the fastest build times, but way faster than building all of this. Or than like all place and route and everything if we were to do this only with Verilog. So that's pleasing. So all we know now is that I think that was just built in with that package. We still need to actually make sure that this is generated. And I don't remember where that's done actually. I think I need to go into main because I think we do Xenowing generate. And so the Xenowing module, yeah, this actually invokes all these generate functions. Yeah, and has all the boot ROM and program ROM and everything here. So I think this is where we ultimately need to do this. So this needs to include use crate color thrust like this. And the code here is going to start getting a bit messy. Well, it's already messy, let's be honest. But we need to go into the interconnect. And so I made this Buster module, and the idea behind that is it's like this hierarchically composable bus unit. And I think if I open draw.io, which I haven't done in too long, I think this will do not want to install a new version yet. Dev projects Xenowing doc bus topology. Here's our beautiful diagram. So yeah, here we have this sys bus, and this isn't entirely complete in terms of what this is going to be, because I think like this DMA has access to these different buses. Actually, I think everything will go through the sys bus, which I think is going to be 128 bits. Probably is already because of this bridge. So that's actually a difference that we'll have to make, but I'm going to refactor that a bit later. I'm going to hook this up because right now this has a couple different like ports. This color thrust version here has 2 different ports for reading and writing. The registers and the color buffer. And I might end up mapping both of those as separate ports here, as separate replicas down here. I think I'm going to do that initially, but then I'll change that later. So what that means is that this interconnect, which actually generates all of this stuff, right? So here you can see there's the CPU. This is a Buster module. This is a Buster module. And so the sys one in particular, I don't remember what all these arguments are. Oh no, I didn't find this definition. This completion stuff is not the best still. But anyway, mod name, num primaries, num replicas. So in this case, there were 4 replicas. I think there's not that many hooked up. I think there's only 3 hooked up, but there's space for another one. And I think we have to bump this up to 8. I think this needs to be a power of 2. I don't know if that's enforced anywhere. But that should be. Oh, actually, I don't think that matters. Oh yeah, because it even figures out like leading zeros here. Well, it does that for primaries. Replica select bit width. Is that just a parameter now? Yeah, it is. Okay, so it doesn't do any bounds checks to make sure that's correct, which I guess we can do better. But that's fine. Anyway, I need BIOS ROM, LED interface, and UART interface. Oh, this is old. That's why there's 4 here. Because I have the boot ROM and then the program RAM. That's why. So I think all 4 of these are part of the... All these are replicas of this sysbus. This also is a lot of copy paste that I could just refactor later. And I haven't because I don't need to. But I should. But actually, this is kind of interesting. I left replicas. Primaries, replicas, adder bit width, and replica select bit width. Yeah, these need to increase. This can be 5. And I'm actually going to change this just like this first. Because this is going to end up changing some things. I'm also going to... Well, I'll keep this at 4, but I'll increase this to 5. So we'll end up essentially with double the amount of replicas here. But then I think this is going to end up changing the memory map. Hey, Frizzy. Yeah, long time no see. Good to see you. So I think the way this works, you can see here it takes this address bit width and then pulls off this, yeah, for the remaining addresses. I think I can actually do 8 here. And I think that simplifies things. It means there's more bits needed than needed to actually do that check. But you can see the reason why I like those multiples of 4 is because like this one here, the CPU, I think also uses 4 bits for that to select one of its 2 replicas. And the reason is that then in the memory map, it uses a full digit in these hex values to determine which bus it hits. So in this case, like the sys bus is prefixed with 0, and then this DDR bus is prefixed with 1. Or the DDR3 interface. So that's kind of the idea. And so then by having more bits here on program RAM and these system regs, at 0, 1, and then 2 and 3 are both things for the system regs because I have this LED interface and then the UART transmitter. And then I can do 3. Oh wait, I'm wrong here. 4 bits is plenty. I don't need more bits here. This will give me 16 different ones. So actually, yeah, this is fine as is, right? How long's it been since I looked at this code? That code in this Buster thing, it's been about 10 weeks, I think, since I looked at it. So from 4 on, this will be, I don't know. I'm going to do this for now. To do. I'll even put it here. That's funny. Actually, I won't do that because I'll forget that. This will be color thrust. But again, I think I wanted to have this as 2 separate buses for now. Any reason I don't leave yourself with breadcrumbs, code comments to make it easier? I feel like I documented this enough for me. I feel like I leave comments in a lot of places, but maybe not as much as I could. I don't know. There's no reason. It's just, it works enough. I don't feel like this amount of discovery that I've had to do again today is an unreasonable amount. especially for a personal project. So yeah, then we're just going to basically copy and paste this again. So yeah, this will just work if I just turn this up. So this will be 6 now. And then this will have everything here generated correctly. So all these 3s become 4s. And then this will, instead of UART interface, this will be color thrust regs. And then we'll do the same thing. This will be color thrust. Color buffer, is that what I called it? Yeah, color buffer. Whoops. And I'll rename regs to reg because I feel like it. Anticore, yes, I do my graphic stuff in Rust, especially if you're referring to the like 64Ks that we do as Logicoma. All that's all the visuals there are Rust, and a lot of shaders, to be fair. A recommendation for getting started with risc-v. Honestly, I just read the spec, which I thought was pretty good. I think there are some decent tutorials at risc-v.org or whatever. But I just read the instruction spec, which is, I can show you. If you go to risc-v.org, which should load here, there's these spec and support. I don't know why this is so slow right now, but in specifications, the ISA spec, like this unprivileged spec in PDF here, for example, this is a great introduction actually, because there's some like rationale about the design choices in like the preface and stuff. I mean, at least for me too, like I was trying to implement this, right? So this is where I started. Like it was a natural starting point. And then also there's several parts in the spec where there's these little notes at the bottom where they kind of talk a little bit about the history or like why they made certain decisions. So I think that's really nice. So I thought this was a good read. In terms of crates, do I use for graphics? We basically have to roll our own for everything because it's for 64K. So like we can't rely on any of the existing crates that have an STD dependency. So we rely on core, which basically means we don't have much other than some like pointer arithmetic and stuff. And then I wrote my own allocator that then just uses the Win32 get proc heap or whatever it is, get process heap and alloc there. And then for graphics, we have our own OpenGL bindings. Thanks for the follow, Esden. So it's all pretty custom, for better or for worse. But that's kind of the name of the game in 64K anyway. I think that's pretty normal. No worries, Anticore. And then our synth, you might have found it already. I don't use alloc-vec. I didn't know there was an alloc-vec. I rolled my own vec. I didn't know that existed. I have to check that. Yeah, there is an alloc-vec, but no, we don't use that. I don't know how I missed that detail. I should check that out though, and see if it's not bigger. I mean, it might. Well, I'll have to check that out because obviously then we could get rid of some code. I wonder how long has this been around, by the way? Because it might be that this didn't exist when I tried this. Because we started that whole journey 4 years ago. But anyway, it's worth a shot, but it might be bigger if it's doing a lot of like error checking, whereas the vec that we made doesn't do any of that, which is smaller. So I'll have to check that out, but anything that can help us remove code is good, so I'm glad you mentioned it. The custom allocator thing that we did was also fairly recent, actually. Or it wasn't fairly recent because we had to do that at some point anyway, but like, or actually, I'm a little fuzzy on the history. I'll have to think about that again later, but like, the way that stuff has been bootstrapped with the lower level Rust has changed a bunch over the years, and we've had to update that as we go, which it's actually been quite stable since like 2018, I think. But like when the custom allocator thing came out, we had to catch up with that. Some error handling and some panic details have changed a little bit too. Anyway, that's very, very far from what we're doing now. I'm going to build this. It won't build. It won't work. But I just want to see that we get the correct error. Yeah, so here you can see cannot generate code for module top because module Xenoing contains an instance of module interconnect called interconnect, whose input color thrust color buffer bus read data is not driven. And that's correct. Because now this is the side of the interface that we need to connect to the actual color thrust module. So then we have to go up into Xenoing. And I'm going to follow this pattern here. So I'll do color thrust generate C. And then let color thrust is m.instance of, it's going to be called color thrust, and it's going to be an instance of the color thrust module. Yes, Freezy. I mentioned, I think 2 or 3 times that I know that I can make this smaller. I don't think I'll do it with macros because all this is metaprogramming anyway, but anyway, yeah, I'm well aware of that. I'll do that later. But this should have built. Oh, we probably just didn't use color thrust here. No, that's what this is. Oh yeah, that. I know I didn't initially, and that's because I didn't know if this is the pattern I wanted, but now I think this is a fine pattern, so then I'll definitely put this behind functions, which will definitely help. Yeah, there's a lot of like, this whole hardware project is kind of crazy because like there's my own HDL compiler, and then that's used at build time to generate Rust simulator code that's then also like pulled in. So there's a lot of things that are meta in weird places, but I don't know. I think it's a cool approach. So now Xenoing contains the same thing, basically, same error. But now we can start actually hooking some of this stuff up. So yeah. Hey, Dark Second. Yeah. So again, the bus that I have for the color thrust now, it doesn't quite match this interface. But I'm just gonna hack it. It's gonna be fine. So I do color thrust dot drive input. Ooh, yeah. You know what? I might actually refactor this RTL to have the proper bus signals. I should have done this sooner. That's kind of annoying, actually. Maybe in that other project where I had just the sim harness, maybe I should massage it there and then come back. Maybe that's the easiest way to do this. Whoops, I didn't mean to close that. Because like also this kind of code can be shortened a lot too. Because essentially you're connecting parts of a bus from one module to parts of a bus from another, and this is the same pattern every time. Yeah, and this also has this like delayed read kind of thing. This read data valid. Okay, yeah, I'm definitely gonna refactor the bus in the other project. So this is why I said we may not get there today. This is the kind of thing that I foresaw, which is fine. I'm not really in a rush. I'm just kind of working towards the most motivating thing here. So if we go back to this little trim project, which is this little minimal version here. So we have this build script here. So I'm gonna end up copying this RTL again, which is fine. I like doing these kind of throwaway projects and just getting something to kind of work and then put it in the real thing rather than fight with the real thing all the way down, because I feel like I'm like removing distractions and then focusing on one thing and then put it in the other, which is also why I didn't push this little trim project. Baby steps all the way. It's way easier for me. But again, it's the wrong module. It's hard to keep some of this stuff straight. Let's see. Yeah, build. So this is the RTL, and then main is what I wanted, because this is where it's actually used. So this stuff is going to need to change because of this interface. I think what I want to do is first I'll make I'll only refactor the register interface. Or maybe it's easier to do the color buffer interface. It doesn't matter. I have to do both. But yeah. And actually, I'm still going to keep these as like separate ports anyway. So both of them I'm gonna have to do. And I think also, I just want to check one more thing here with this memory map. A lot of pieces here. Because here I have like this LED interface, or for example, this UART transmitter, status and write. All of this is aligned to individual words. Or actually, let's look at for example, the program RAM, which I think is actually defined in the Xenowing RTL right now. Oh, that's what I did. I split it up into 16, right, because this bus, program RAM adder, what's the data width here? Sys, and I think, yeah, it's 128 bits already. That's the data width. So I think, let's see. Yeah, we have individual byte enable. So there's 16 of those, and then this address bits matter bit width -1 down to 0, I guess that's going to say. Oops. Yeah, here. Oh, I am just cooking in here, you guys. It's so hot. Jingtron, thanks for follow. Actually, was it in Buster that I determined that with? I think it is. Yeah, there's the adder bit width. Primary is replicas adder bit width. So in interconnect. Yeah, and I made the addresses too to be nice numbers here. Right. So I think this is the key. I think this is 4 bits minus 32, and I think the reason for that is that this is going to be in 16 byte words. I think that's why this is 28 like this. The point being, again, that I think all of these addresses are in 128-bit words. I think that's how this looks. And I think that's actually exactly what it is. I think if I go into the mem map again, yeah, you can see these are actually all 16 bytes apart. And again, I did that to simplify the memory map. So like these really only need to be aligned on actual 32-bit word boundaries, but because the bus width is 128, and I'm doing that for the purposes of, I'm going to make this DMA be 128 bits wide, and that's because my DDR3 interface is 128 bits wide, so to maximize that throughput, ultimately when I get the DMA, it's going to need to communicate with both of these buses at the same time. You can see I made a dotted arrow here because this is how it is connected currently, but eventually this CPU will branch out into the MEM and sys buses. And the DMA will also have access to those. And both these will be 128 bits wide, so we can read from this and write to this, or read from this and write to this at the same time every cycle to maximize throughput. So then these all get addresses that are in those 128-bit words, and that's why I aligned everything on 16 bytes here. Now it's all straight in my head. Again, it's been a few months, but I think this is good. Yeah, my green screen is just a trash fire right now. Again, it's so hard to predict the lighting in the summer here. So that's what it is. If it's distracting, I might as well just disable the filter, but I don't care. Okay, so yes. The point is this actually starts to work out kind of nicely, I think. Because then if we go back to build here and main here, we need to have a certain bus format, and I also have that documented for myself in this gist that I haven't made public, only because I don't think it was final. Might as well be, though. I need to move this into the docs thing in the Xenowing at some point, but it's good enough. So again, bus ready, bus enable, all this kind of stuff. So I'm just going to slowly start massaging this, and I'll do these 2 different buses for 2 different things. That'll be good enough. I'm actually going to open this here because if you guys haven't noticed, it's really hard to read with this big font size. There's a lot of text here, so I'm going to need to use all of this. So yeah, I have this color buffer write enable thing here, but instead of write enable and read enable and have 2 different read and write buses, we're going to unify these. So we're going to have a bus address signal and a bus ready and bus enable, all that kind of stuff. So I think we do this. Write enable. Oh yeah, that's this input. So we'll do dot output color buffer. We'll call this bus ready, and we'll always make that high. So it'll always be ready. And then we'll do let color buffer bus enable is m.input color buffer bus enable 1-bit signal, and then let's color buffer bus adder is .input. And this is where we're going to fudge a bit because ultimately I want to have this color buffer be accessible as 128-bit words, but currently I'm only using 32. So I'm going to interpret the 128-bit addresses, or these 128-bit aligned addresses as 32-bit aligned addresses, which means the reads and writes to this buffer are all going to be like each 32-bit words. It's going to be like expanded, but it's going to reach the same memory. And eventually I'll have to change that. But then to do that, I think I need to change how I organize this memory so that I can only write, or that I can write just 32 bits at a time from the pixel pipeline. Again, if I have more pixel pipelines in parallel, then I can do 128 bits at a time, but that's a bridge I want to cross later. A lot of things to get this right. But yeah, this bus adder, I think I have a... Don't I have this actually? Where's the mem? Yeah, tile pixel bits. That's how many address bits I want here. And then those are the common signals, and then we have the read signals, which I think we need to actually register. And I'm probably going to copy some code here from helpers, which eventually I'm going to remove. But I have this register next thing. And we need this. We need both of these for later. I just copied those because those are in helpers in the Xenoing RTL, but not in this little tiny project. So I'll just copy those here for now, instead of like adding a dependency and all that. Yeah, so the idea is that now reads will change. I think I'll write the read path for this first. And so you can see here, I have this read here. And so I think I'll always do read data from this read port. And this read port is going to come from this adder is going to be this color buffer bus adder here. And then read enable is actually going to be something else. So we need, in addition to the adder, we need color buffer bus write. For whether or not, so we have enable and write, and that's going to determine whether or not it's read and write. I also am going to be a little pedantic here and just make sure we're ordering things the same way. So enable, adder, write data is how I have it set up there. Enable, adder, write. Good enough. And I'll also do this. And this will be 32. Eventually that'll be 128, but we're going to make this 32 for now. And then this write port here, yeah, that goes here now. And this write adder thing also becomes this adder. So it's either going to be written from the external port, and this color buffer bus write enable, this is going to be color buffer bus enable and color buffer bus write. So yeah, we're writing to this color memory if the bus is writing, or if we're writing from the rasterizer. That's what all this is. And then the address is going to be determined based on if this is a write from the bus or not, the address and the data that goes in there. Otherwise, it's going to come from the rasterizer. So that's what this muxing stuff here is doing. Probably a nicer way to write this, but again, things will clean up as we go. And then, so I think that's it for the write path. And then we have the read path. Yeah, so we have ready, I guess I usually do after this. So I'll put that there. Actually, I'll have this at the top still. I thought that was okay. So this is just always ready. There's no reason for this to ever block, so that's fine. And then, yeah, we have read data and read data valid. And so read data, I'm basically always gonna do this read port, which is actually already gonna have the cycle delay. So we probably actually don't need this one. I think we only need this one, but I'll leave them both here just in case, because I don't care about making a mess here. Yeah, the data, we want to reflect the data read from this port. And so we're always going to point that at this address coming in from the bus. So we may end up with a read and write at the same location, which could be fine. That has guaranteed semantics. And then for the read here, then we want color buffer bus enable and not color buffer bus write. That's what a read is going to look like. So that's going to be the enable logic for that. Is that Yesipie? Did I read that right? Thanks for the follow. And then the read data valid is going to be a little bit different. This is going to be color buffer read data valid. And the data valid is always going to be true the cycle following a valid read. So we're going to do the same thing here. Bus read. And we're going to combine this whole thing. And so this is going to be, I think the way I wrote this, I need to move these into Kaze eventually, but I think I do reg next with default. So I give it a name, next in default. What did I call it again? And don't I also need to give this the module at the end? Yeah, there it is. And actually, what have I been doing with this before? Have I been adding reg at the end of this? I don't think so. I think I use different namespaces for these, but I just want to be sure what I've been doing elsewhere. Yeah, I do the same thing here. And then the default value should be false, because we don't want this returning rogue data like on system startup. So we want a default value for this register. So essentially, this valid signal should be high the cycle following a valid read, which is also when the data from this read port will be ready. So that's already hooked up here. So that should do it for this part of the interface. Oops, I forgot the module as well, which it needs. Again, I need to make that something in the HDL, but not yet. And now all of my color buffer reads and writes here are wrong, because now the interface is different. So again, if we go to target, build, probably this one. Yep. So you can see here, now we have our new inputs and outputs. This I am gonna put over here now. And if we go into main, so now we need to do this read and write differently. So I'm going to do writes first. This is a bit easier. So we do, actually the first thing I'm going to do is set some of these default values. So this will be color buffer bus enable is false. And then the other signals don't matter as long as this is false. That's what we want. And then when we want to do a write, the first thing we do is we're going to pull that high. And then we need to do self color buffer bus write is true. Also at the end, we're going to make this false. So we're saying enable and write. We should also assume that this is not always ready, but we know that it is, and that's fine enough for this little test. I don't really care. So yeah, we enable ready. We enable write. And then we also want to do the adder. And that's again this. So this is now just bus adder. And then this should be bus write data, I think. And that's this 32-bit value. And then we're going to assert that for our clock cycle and then turn this false. And again, normally we would have this handshake where we want to check that ready is true. But I know that it is in this case, so I'm going to ignore that. And then for reads, we want to basically do the same thing. We want to set enable, we want to set write to false. We want to set the same address, and we don't care about write data. And then we're going to, again, do prop and then tick the clock and then propagate out again. And again, on the cycle following the read, we're going to expect that it is valid. Again, we should actually wait until this is true. In fact, we could do that. We could do that. Let's do that while self dot color buffer read data valid. Then we'll do self dot pause edge clock and then self dot prop. So actually we'll issue it. And then we'll disable the bus. And we're again going to assume that that went through. It may not. We should probably do that handshaking, but that's fine. And then until we get read data valid, we do this. And then once that's valid, then we can do return read data. And actually, we don't need to propagate anything anymore. We used to do that in the old code path, but now it's just this. So I'm guessing this will work. Not too terribly difficult. Yeah, there it's working still. So we basically want to do the same thing. I actually do want to do this thing where we make sure that ready was asserted. So for this, we want to do this while not self dot this bus ready. We're going to do the same thing. Tick the simulation until it's ready. Because we want a cycle where enable's true and the bus was ready. And then once it is for a cycle, that's when we tick the clock again and then also set it to false again and then propagate. So I think this is the correct logic for this. And for writes, it's going to be the same. So yeah, this still works, which is great. And then we're going to do the same thing for these register values here as well. And we're going to assume that these addresses are all like 128-bit word aligned. So we're just going to read the address as is when we do these comparisons. But yeah, we want to do this same bus here. So yeah, So we called this the color buffer bus, and I'm gonna call this the reg bus. So we'll just do some of this. This reg write adder is gonna be, oops. Yeah, reg bus write adder. Reg write data as well. The reg bus write data. And reg write enable is going to be reg bus write. And then we also need reg bus enable. And also here, I'm going to do the same thing with this color buffer bus that it's always going to be ready. At least for now. And then I'm also going to do this thing that I did here, where I made this write enable thing by combining those other parts of this, just because that was easy. And actually all the parts where I did this should have actually, they were correct the way they were before. All these writes here. And I think also the read, yeah, it just returns busy. But then we need to be careful with the read data valid signal. So this will be reg bus read data, and that will just always return this busy reg, which is fine, and concatenated with a bunch of other stuff. And then again, the read data valid, this is where we need to be a bit more careful. But this again is just going to be reg bus enable and not reg bus write. So the idea is it will the read data will always just reflect this value, but then it will only strobe that it's valid on cycles following ones where we detected a read. And then default false, which is very important there. I think that does it. Isn't much that it does actually. We're actually busy here. We probably need some handling there. I think I might have had some other logic down here. Yeah, that's this one. Because this one's not correct now. We need this to match this reg bus write enable. And this again toggles busy and then loads all the initial states for when rasterization starts. That's what's happening there. That's once you get a write to this particular start address. And I don't even check the value. I just check that there's a write to that, which is fine. Those are often called strobe registers. So yeah, again, we need to fix like the bootstrapping. But then this interface, then we'll know that we still have a working rasterizer, and then this interface that we use to interact with it is going to have the same kind of bus that we do for the rest of the system. So it's going to be easier to hook up into everything else. And again, reads and writes now look basically the same, because again, these are now the same kind of bus. And we want to be a bit careful. I'm actually also going to reorder these now, because I think the way they're declared in the RTL is the opposite. Not that that matters, but that's just the kind of thing I like to keep up to date. And again, eventually I think all these will be accessed via the same bus, but For now, this is fine. What? Reg read data? Did I just make it reg and not reg bus? Or did I do this somewhere else too? Main 33? Oh yeah, reg bus adder doesn't make sense. Or yeah, it does. I just didn't do that right, did I? Yeah, because I have right adder. And that is not what I want. That's not correct. So again, enable adder right, I think was the order that I had all this in. Yeah, there's also these byte enables, which I'm probably just going to drop. Probably just going to ignore those for now. Yeah, we also have this reg read data, 47. Just be reg bus read data. And these ones down here too, this color buffer read data should be bus as well. And since we didn't get any errors, I probably named those other ones wrong. Yeah, see reg bus. Here I have color buffer bus, except for these ones. And this should work again. Except self reg bus adder is adder. What did I mess up there? This was 33. Oh, I actually ignored this address. That's fine. Great, that works. Easy. So now this same code should be ready to copy paste back into the real thing. Again, what I need to do eventually is to hook up this little sim project that I have as a proper sim project over like the proper RTL and everything. But this is just what I made on a Tuesday. Yeah. That probably works. And then we need to actually hook it up. Which I think I meant to copy basically this. There's actually two buses here. So again, if we go to interconnect, yeah, we have the color buffer bus and the reg bus. Did I name that like that? Like color thrust. Reg bus. Yep, I did. We need to do the same thing here for all of these signals. Bit unorthodox to have two buses on this one module. That's what's kind of weird here, but it's only me working on this, so I don't care. And I probably will fix that later. Make this go through a common bus. Or maybe not. Who knows? But I probably will, because I think there's a lot of lines here. Also, some of these, I think, like the read data, is probably going to need to be expanded to 128 bytes, 128 bits, I mean. So I'll probably end up doing that here. So yeah, instead of reg bus here, we're going to have the color thrust, color buffer bus, I think. And yeah, if I run that now, Wing, I'm doing it via this blaster top level interface, which is fine. Yeah, so now regnext with default here is wrong because we need to use the helpers, which I thought would have been in there. Interconnect maybe has it, or Buster. Or not? What the hell? I thought this would have. Buffer? Which one of these has helpers? This one. Create helpers star. That's what I wanted. Yeah, and now it says attempted to drive reg bus adder on instance color thrust, but this input and the provided signal have different bit widths respectively, right? So this reg bus adder only has 4 bits, but we drove it with a signal with 20 bits. That's what happened there. So then what we can do, I think, yeah, it looks like I tap off like a smaller number of bits on this level. Maybe I don't even do that there. Maybe I just expect an entire, like the whole bit width later, or the whole bit width to be provided by the module. But what I'm going to do for this is just this. So reg bus adder, and then I can do dot bits. In this case, it was 4 bits, so 3 down to 0. And now I do this, and the compiler will tell me, my RTL compiler, or my HDL compiler will tell me all the things I need to do wrong here. So now it says bus write data, which is true, because again, we wanted to tap out the bottom 32 bits. That's what's going on there. And I'm guessing the read data is going to have the same issue. And maybe also these byte enables. Did I even make inputs for that? I don't think I did. I think I just ignored them. Yeah, drive an input called this, but no such input with this name exists on that module. So I'm going to do that about it. The byte enables are from the primary to the replica, so it doesn't matter if we just don't use that signal. We don't need the module to care about it. Attempted to drive an input called color thrust reg bus read data, but this input and provided signal are different widths. Yeah, so again, the read data here, this is on the interconnect, so we need to essentially expand this out to 128 bits for when it's read. So what I'm going to do there is m.lit .concat. And so now here we can do, I think, did I also add in Kaze like a prepend function for this? I need to look that up. This is actually properly documented, this API, which is nice. So then I can go in, for example, signal. I think I added a prefix, so maybe prepend. Did I do append? No, but I did concat. Okay, maybe I didn't do prepend and append. Maybe that was just a thought that I had. Concat's fine. And so then we can do 0, and then we're going to make this 96 bits. So we just have a bunch of 0 high bits, and then the 32 least significant bits are the ones that this is actually going to return. So that's how we're bridging that 32 to 128-bit bridge. So now we're on the color buffer bus adder, but now this has 8 bits instead of 20. So we're going to do the same thing where the bus adder dot bits 7 down to 0. And actually, I'm going to go ahead and start fixing some of these other issues that I know are going to come up. So this bus write data is also going to be the same thing here, 31 down to 0. And then I also know we're going to do this for the read data. And Kaze will check especially bit width mismatches. Like that's one of the things that I just hate. Oops. Yeah, you do concat. That's one of the things I just hate about Verilog and System Verilog is that it will do like automatic widening and narrowing, just like C does. You can probably set up like linters to catch that stuff, but in this case, I wanted my HDL to be very strict that all bit widths need to match. And so if you need to like upcast or downcast, you actually have to explicitly take a given number of bits or like concat more bits. Okay, so this actually built. Whether or not it works is something else. But I think we should just kind of go for gold here. So I'm getting kind of excited now. Let's see. We go back to this trim project. And we probably have to like copy matrix and vector and stuff, I think, just the way I wrote this. It's essentially this loop that I want to copy. And I don't necessarily need to do 5 triangles. It doesn't really matter. But yeah, I'm just going to copy this. Also, I kind of want to have a buffer here to visualize the output. I might actually make a little window here in the Xenowing Blaster, which is going to be, again, this is kind of why I wanted to have that device thing abstracted, but I also don't know how that abstraction is going to look yet, so I'm probably just going to hack the blaster thing for now. We might actually get this today. That would be really exciting. I think, though, actually, before I do the window to visualize the output, I might, well, because I need a back buffer too anyway. Yeah, I might as well just make this happen. So let's do a bunch of this stuff then. Let's go ahead and add minifb and rand to my dependencies in the Xenowing Blaster. Okay, and then we're gonna go here as well, and we don't need any of this open. Main. We're gonna go ahead and add some of this stuff here. I'm actually gonna pull this down to where you guys can't see it, but where it's gonna make it a lot easier for me to copy the important stuff. Can I not do that? Can I open this in a new window, please? I don't remember how to do that with VS Code. I say like I ever actually knew. Okay, well, Control N, no. Is it Control Shift N? This new window? Yeah, and then can I drag this down there? Man, what is going? Some things are just so slow on my PC right now. It's frustrating. Okay, that'll work. Good enough. Don't care about updates for stuff. That's not what I'm working on. Yeah, so now we want to copy some of the stuff here to the Xenowing Blaster code. Go to main here. And I'll just stuff this here. Literally anywhere is fine. And yes, I am also going to do this matrix vec2 and vec3 stuff. That. And then I'm going to have these other modules. And I'm just going to copy those over. We don't need all of them either. I'm just going to be lazy about it. Projects. Xenowing. This is kind of a little thing for this project, but man, I'm getting excited that this might actually work today. It will be my first rasterizer on FPGA. However basic, that is actually very exciting. So I think that's why I'm so pumped about this. So now we need a back buffer and a window. And I'm not even going to have a loop that checks while the window's open because I don't want to. So I'll just do this in main here. Create a device, then make a window. And then I'm only going to update it once we do this kind of loop here. So now I want to actually do a lot of these prints here from the host initially because I do. I think that's going to be smart to do that. I'm going to comment this out for now. And do some other stuff. So there should be enough space to buffer all the commands that we're doing as it's writing all the registers and everything, because the way I hooked up the UART stuff is I hooked up a FIFO between the UART receiver and like the interface that the CPU can access. So I think there's 120 or 256 bytes or something relatively small, where it will be able to buffer all of that data. So if it's not able to read the commands fast enough, which it should be able to because it's just doing basic memory writes here, but it's not able to do that, at least we'll have a bit of leeway. So I just want to send all the commands and then do all these prints. Now, one of the things that really sucks is the way that I did this. I'll probably change the program to like initialize the rasterization loop. I might actually like add a specific command for that. And the reason is I kind of want to figure out how many cycles it takes. I know roughly what it should be. It should be, I think, 1 cycle per pixel. So it should only be like 256 cycles, but then it'll be plus or minus a bit because of everything else in the system between the rasterizer and the CPU and all the reads and writes and cycle offsets and everything. So I would like to see that it actually is. And the other thing is here, because I think the top level code is just going to wait in a loop while it's reading a register, and it's going to have to round trip all the way to the system and back every time it does that. So I think it's going to be real slow. But yeah, I don't know. I want this to work, so I'm gonna try this. Let's see. Yeah, we want to have this loop here. I already did that, didn't I? Okay, great. So here's what I'm going to do first. Again, I want to write out like everything here because I want this to be very explicit as it's writing everything out. I'm going to do something like this. Yeah, this is going to be so slow, but I think it's going to be really fun. And so then now we need this rasterize triangle function, and then that also needs to do actual register reads and writes. which then we also need to abstract. In fact, actually, it's the only place it calls this. And since I'm just kind of hacking this together right now, I'm just going to copy the contents of the function. That's going to be fine. Yeah, none of this pipeline is programmable at the moment. Compute shaders maybe in like 10 years. That's ambitious, let's be honest. Let's see. I think I need, yeah, this is already mutable, which is great. That actually doesn't need to be. I don't know why I made that mutable, but whatever. Yeah, all this should be fine, except this stuff is all broken now because, well, actually, we just don't need to do this, do we? Indeed, Freezy. Let's see, yeah, all these color thrusts dot right reg or whatever. That all goes away, and we're just gonna do right reg. And I think I do need to change some stuff for all these as well. First of all, I think I want to send it the device, I guess, because I have, yeah, device.read or write byte. And we need to like forward these result structs here. Yeah, it's programmable in the sense that I can just write a different pipeline. Very true. Transform. Yeah, so I want to do, first of all, I'm going to have all these reads and writes here. I'm going to do this. And then I'm also going to have it to send the device. What do I do here for this? It's a boxed device. So I probably need to, I think I need to take a reference, I think. Also, these addresses, like the way I'm going to do this is going to be a bit different as well. Yeah, and also these write color buffer and read color buffer, these also are going to need to be changed as well. And do these need to be mutable? This device, yeah, they both do. Read and write byte both need to be mutable. So I think actually where I did this ampersand device thing on all of these, I think is going to be wrong. Also, again, you'll notice I'm still doing this stupid thing where I'm copying the tile memory way too often, like this color memory. And who cares? It's fine. Yeah, this also I'm gonna do in mute device. Actually, this one I might just inline again because it's just in one place. And it's totally written in terms of the other things. So that's kind of nice. Like this. Again, what we write here doesn't matter, but that's fine. Yeah. So let's go ahead and look at these. going to do this. So the first thing I'm going to do is function write word. I'm making such a mess here, and it is totally fine. So then we're going to do something like this. And I'm going to stood out. This actually comes from here. Yeah, I don't care. Yeah, we need the adder and then the data. And it's basically gonna do, it's gonna be this. Okay, I'm going to do also read word. Oh, I ordered this weird. Whoops. I was going to indent these because I'm cheap. And then we need to actually get the data. So this one, I'm actually going to have it print twice. Oops. Just in case we read or we write and then we don't get the read yet. So we want to get the read. Then here, once we know we've actually read all the data, actually should be okay data, and this should be okay like this. For when it's completed. Okay, and then we can write read reg and write reg in terms of that. So read reg, we're going to do, first of all, these are also going to have these device parameters, and they're also going to return a result. And so what this is going to do is it's going to do read word. And the address is going to be adder times 16 plus the base, which I think, again, we determined was going to be this offset. And write reg is going to be basically the same. Like that. And then we have read color buffer and write color buffer, which are basically going to be like this. And now these are going to be 5s. Oh, maybe that works. Maybe not. We'll see. Did I do the update at the end? Yeah, I did. Update the window. And this has to build everything again. I'm gonna be so stoked if we get this to work today. What I fear is that we're gonna start like hanging on reads, and have to start some real deep kind of debugging stuff. But I actually suspect that this will work, because again, we've tested this hardware unit isolation. Ooh, what did I do wrong there? Read reg takes 3 arguments. What? What did I do? Oh yeah, doesn't need and self. Whoops. Full of shit, Jake. Doesn't make sense here. Device not implemented for box dyne device. So that probably means I think what I need to do is dereference this. Thanks again for the sub, Dark Second. Really appreciate that. I like those custom emotes that it unlocks, so I showed that as well. I think we do this. Oh yeah, and then this matrix stuff. Oh yeah, and then these also need to be dyne device? Right, because I'm doing dynamic dispatch there. I'm still not used to that in newer Rust. And I should fix that. But yeah, this should be dyne here, I think, for all of these. But yeah, then because I pulled in this like vector and matrix stuff, of which I think I'm only even using vec2 right now. Yeah, so these are unused. Also like tile dim and stuff, so we need to actually pull that in as well. I think I already added RTL as one of the dependencies, which is great. And so then here I can do use RTL color thrust star, and I think that will get us those defines. Okay, first of all, let's just take this one at a time. So 272. This was this one. Yep, that's that. And then window, yeah, because we need to include, or I mean use some of the mini FB stuff, and same with the RAND stuff. We got to do that too. So we'll go up here and include some stuff. Just build it again. Yeah, we need vertex, which is some struct I made, which feels a little silly because it's just that, but I didn't know how far I'd go with that other test, so that's why I made that. Rasterize primitive at 463 is not in scope. Oh yeah, I replaced it, or I meant to replace it, but I just added that. Yeah, mini-FP is great. It does exactly what it needs to do. It's gotten borderline a bit feature creepy, but nowhere near to the point where it bugs me. It's just that as soon as you make a window, like there's so many things you might want to do with a window other than just have pixels. So like it's almost natural that you would start expecting things like even just mouse interaction and keyboard interaction is kind of be out of scope a little bit in a way. Oh. Oh my god, this is slow. But this might be working, you guys. I mean, it's getting data from the sim, the system in sim. Okay, I'm gonna do a couple things first. I'm gonna do two main things. First, I'm gonna reduce this and just make it do like one tile, which hopefully MiniFB is okay with this, with a window this small. And the other thing I'm gonna do is make it only do one triangle. Like that looked really good though, the fact that it wasn't freezing or anything. You know, we were reading data. Oh, you guys. I can't move the window because it's too slow. But it's drawing triangles. I can't move the window. No. It's too slow. I can't show you. This is so stupid. But it's drawing triangles. I can't show you. Oh, wait. It's so slow. I can just snip it for you. Can't I? Look at this. Oh, this is so cool. Man, so many things just have to just work to do this. Like, how cool is that I was able to add another... Oh, yeah, window capture in OBS. That would have been smart. Oh, no, I resized it, too. Whoops. Okay. Actually, window capture in OBS is a good idea because then I can... I'll do that next because then I can scale it. But I'm actually going to try this on the real hardware now, which should just be this. Oops. Crazy, you guys. Crazy. It's faster. Uh-oh. Oh, no. Is it frozen? Oh, I sure hope not. Because that's the worst when there's differences. Oh, no. I know why it doesn't work. I didn't recompile the hardware. Of course. That's stupid, Jake. So I can't test that yet, of course, because I changed the hardware. So then it was reading into the void, and then, of course, it froze. Okay, so I'll add a display window capture here for you guys. Oh, this is sick, you guys. Oh, it even picked the right window. Oh, this is great. Look at that, you guys. Look. Oh, wait. Why did it get all scaled weird? And why did it... I accidentally flipped it. Okay, I don't know why this got scaled so weird. Whoops, that is not the right way to do that. Is it? Can I just do one axis? Control click maybe? Shift click? There we go. All right, so this is actual triangles being rendered to a single tile. How cool is that, you guys? Oh, that makes me so pumped. Oh, that's so cool. Okay, so this is so funny. All right, here's what I'm going to do. This may work if I go here and I do make RTL. I think everything will work, and this will generate all the Verilog for this. No color thrust in the root. What? Then how did this work? RTL, lib, color thrust. Right? Did I not make it public or something? right there. Oh, yeah, because this goes from main. That's why. Okay. So mod color thrust. That's what it is. I know the output is like all up in this stuff. Guys, this is so cool. Okay, so that built, which means we should now have color thrust here. But we don't. Why don't we? Xenoing generate. Yeah, that should have generated this. That's concerning. Oh yeah, because I didn't run the program. I just built it. Did I? Wait. What's my make file again? Is it generated RTL? Yeah, generate RTL. Make generated RTL. That should actually run it. So now this generated thing should be updated with color thrust. Look at that, you guys. So here's the generated Verilog, which I haven't tested yet. But I'm going to be pretty fucking pumped if this works. I'm getting so excited, you guys. Okay, so now I have to open all this Xilinx crap, which was, I don't even remember what it's called. Vivado. It's called Vivado. Guys, I'm getting so excited right now. As the sim is still generating data. This is so sick, you guys. And I'm expecting Vivado to take forever. Also, I need to open this Tanagra thing, which is like the board management software that I have, which always uses way too much CPU and it's buggy as hell. But it works. And yeah, it's available. So we'll use the virtual device stuff there. Guys, this is really sick. Really sick, you guys. I'm so pumped. Like, this is so cool because this is just like, this is a really shitty driver that's reading and writing registers all the way over UART. And then that's just doing those basic reads and writes, which I did in the program running on my CPU in the system that I now hooked up a rasterizer into. And it actually does the thing, do the thing. And it's streaming data in and out of that memory too. Oh, this is exciting. So it should be enough. Now, hopefully, there's something that might just totally shit on my parade, and that would be if we like break timing constraints or something now that we've added this stuff to the design. So I'm a little concerned about that. But let's try it, right? So generate bitstream, go for gold. Come on, go, go, go. Generate bitstream. And just so I can be sure, this should have Xenoing, and in here we should see, yeah, color thrust is there. So it found it in the Verilog at least. It didn't find any errors. Because also, how sick is that? I didn't write a line of Verilog today. That's pretty nuts. I'm so happy I have this RTL, or this HDL. Yeah, it'll be fine. I'm not worried. You can see too, more of these are populated when it reads those words from the color buffer. Ooh, I had the wrong number of digits, by the way, in my output here. I'll fix that, and then when we run against the actual hardware, it'll be fixed. But I want to leave this other one running while I still can. Because it's so cool. This is so cool, you guys. Main, and then it was in here. This should be 08X, and this should be 08X, and these should be 08X. But this right here, by the way, like, this is the whole workflow that I have envisioned the entire time I've been working on this project. Like, I would sit and I would work on a new hardware unit in isolation, right? And then I would make sure it implements the right kind of bus. And then I would just plug it into the existing bus architecture, which I already have, and that's why I made all that reusable stuff. And then it would just work as long as I made the software work, which in this case does that over UART, but like you kind of see the point. Like I'm able to sit here and iterate in sim until it works without too much headache. And then it should just work on the device. And if it doesn't, I'm going to be pissed. Might even cry a little. But if it does work, man, I'm going to be pumped. But of course, I'm talking a lot because this will take several minutes. So you can see it's been a minute and a half. And right now it's just synthesizing. And this isn't particularly complicated hardware. Of course, it will get more complicated, but it still won't be that complicated. But yeah. I think usually the implementation stage usually takes a bit longer even, and that hasn't even started. Also, I'm using a lot of CPU on like streaming and stuff, so wouldn't be surprised if this took a bit longer than usual. I think it takes like 5 minutes normally because I don't have any like memory controllers or anything here, so it should be pretty basic. Like basically all of this is there's of course all of this generated code for the Xenowing itself, but then there's a bit of bootstrapping as well that's in Verilog, which I think is in this. If we look in the board files or in the board directory, so in Mimase 7, Xenowing, there's some extra RTL here. So there's just this top level thing. Yeah, this is actually it. There's some sync chains for reset and the UART receiver, just to make sure everything is clean once it enters the clock domain. I just realized again, you can't see this, but yeah. And then that's it. Then it's just the Xenowing, and this Xenowing module is the same one that's bootstrapped in sim with another module called top that just does slightly different bootstrapping. Because the one in sim also will add another UART serializer and receiver, or transmitter and receiver, that it then hooks up opposite to the ones from the Xenowing so that we get a byte-oriented interface at the top of the module. Oh, that's awesome that someone's doing PS1 for Mister. That Mister project's really cool. It might actually be worthwhile trying to target this project to that board at some point. Assuming that we end up with enough memory on there. Because then it wouldn't be DDR, I guess. Or maybe it still is. I'm not sure what the memory looks like on there. But as far as I know, it was SRAM. And as long as there's enough, it doesn't really matter. But yeah. There's some warnings. I'm not too worried about them because I think there's always warnings on here. Resources of type BRAM have been overutilized. We'll try to implement using LUTRAM. I hope that's fine. That's a bit concerning, actually. That one might cause us some problems. Yeah, you can see BRAM is all the way used up, and then a little bit of LUTRAM. That's surprising, actually, that it uses all the BRAM. We're gonna have a look at that. That's actually shocking to me, because we should not have gotten there. We shouldn't have gotten nearly that much usage. So that's something I might have to look into. Oh yeah, 32 megs of SRAM. Yeah, that should be enough for Xenowing. The current implementation is going to have 256 megs, which is way more than I need, but that's the only memory I have on this board is, or the only fast memory like that I have on this board is internal memory in the FPGA and then the DDR memory. So it's quite a lot of memory for this system, but But yeah. So yeah, I'm actually quite concerned about this. And I need to look into that, I think. Oh no. That's crazy that it ended up with this wrong aspect. Yeah, the other thing too actually is that it might have enough memory, but I'm also expecting 128 bits wide memory bus, which I guess I could emulate if that SRAM isn't wide enough, or maybe it is. I have no idea. Or as you say, I can target that DDR3 if that's what it has. This is taking a while, which is somewhat normal, unfortunately. Yeah, it has only been like 4 or 5 minutes, I guess. But yeah, I am concerned that this uses so much VRAM, and I'm surprised because, like, I have that color buffer. I have, like, it must just be the amount of memories, like the number of memories that I'm expecting to be available. For example, to get byte writes, the way I've implemented that in a lot of the system already is that I've implemented them as 8 separate memories each. So I'm wondering if it's just the amount of memories that I'm using, and maybe I'll have to add byte write support to the memories in Kaze to work around that so that we get that mapped correctly. Because I think the individual BRAMs on this board, at least, they actually support byte writes, individual byte writes, but I haven't added language support for that. So I instead implemented it at like the API level where I split it up into different memories individually. Generate bitstream, it worked, right? So I actually expect that we didn't violate timing or anything, which is a good sign. I'm just going to open the implement design to have a bit of a look at this. But yeah, I'm guessing that that's why actually we blew VRAM here, is that I'm just using too many memories, not necessarily too much capacity. But I'm going to need to look into that because at some point I'm going to be using a lot more capacity. Actually, I'm not, because I totally forgot. Actually, this makes perfect sense because I'm using 128K for the main memory right now instead of DDR. So actually, I don't think I need to look into this. I think this makes perfect sense. 128K is actually quite a lot for this board. So, yeah, I think all these are the block RAMs. And then it does say it's spilled into LUT RAM, which if it behaves the same is going to be fine. So I think it should. But yeah, timing looks good. Hopefully that means I haven't underspecified anything. But then I will open up this XVC server thing, which should give me virtual cable. And then let's see if I remember how to do this. If we do open hardware manager, it will allow access to that as well, or for that. And then I should be able to open, once this goes away, open targets, auto connect. And I think this will just find it. Or no, I don't think it will actually. I gotta allow access because of course all the software has updated since the last time I used it. So open new target, that's what I need to do. And then local server, so it should find that. Because I'm running my virtual cable here. I'm gonna be so pumped, by the way, if this works. I think the sim is still kicking. Yep, that's still working. Cool. Okay, this is not going well. I think actually when I do this cancel, like I have to restart the hardware manager. Like this stuff is just so fucking buggy. Worst experience. I hate dealing with these tools. Because this should not take this long. Come on. And Vivado better not fucking crash on me. Ugh. Come on. Okay, I'm killing Vivado. This is annoying me. I am not patient enough for this crap. I think actually you can target this 7 series FPGA from like with Yosis and XPNR and stuff, but I have not looked into that, and I don't trust that stuff yet. Until I can like sit down a few days and actually like do proper comparisons, I don't want to dive into that. Even though these tools are annoying, I at least know they work, so it feels a bit better to use them. Or at least it feels safer to use them. But I do actually think that there might be enough support in the open source world to generate whole bit streams for this device. Yeah, and it shouldn't have to like generate a new bitstream or anything, because that should still be up to date, which it did properly detect. That's great. I'm gonna open new target now. Hopefully this just works. This is usually quite fast. If it's not, and it just hangs here again, I'm gonna be pretty annoyed. There we go. Now we can add this virtual cable. It says it failed, but at the same time, I don't think it did. Whatever, man. Okay, now I'm gonna kill the sim thing. And now I'm gonna program the device, I guess. That should be the right one. In the meantime, I'll start this up, which I hope starts up at the right time. We might have missed it. If that's the case, it's fine, because I'll just reset the device. Yeah, because now we missed the command where it asks for its program. Again, that's fine, because I can just go and reset this. Okay. Is it working? Oh, you guys. Oh, you guys. You guys! Okay, I don't know why this cropped differently this time, but holy shit. This right here is my FPGA GPU actually working. Now I haven't verified that this is actually like correct, but it should be. I don't see any reason why it wouldn't be, and it does look like triangles. That's so sick. Oh yeah. First try. It's actually true. That's so sick. Still too slow for me to move the window. I'm going to do something actually that I think will be really cool. I'm going to kill this. Okay, first of all, I need to take a second to appreciate what I've just done, because I just realized this is awesome. But I'm going to increase the resolution now, because this is a bit faster, right? So let's do by 4. So this is going to be 1/16 the speed. So it'll be pretty slow. And I'm guessing I need to reset on the device again. Right, so it's working. And again, this, I don't know what's going on with this cropping. It's probably correct now, actually, the cropping here. So now I just have to zoom out, I hope. Guys, would you look at that? This can't be the right aspect because the width is not greater than the height. So I think it's still cropped a bit wrong. And I'm guessing looks a bit fat. So I'm guessing if I do this, we get the more or less correct aspect. Yeah, I mean, surely the string output doesn't help, but I'm 100% sure that the bottleneck is sending everything over UART. This is working. And I'm pumped about it. Yeah, it has to serialize. So the way that this tiled renderer works is the back buffer is actually stored on the PC right now, and so for every tile of the screen, I can't really point with my mouse. Every tile that this is broken up into, which in this case is 4x4 tiles. So for every tile, it's going to copy all of the pixels in that tile to the device, and then rasterize a triangle, and then it'll copy it out. And right now, it doesn't do proper triangle lists per tile, so it actually copies in and out the entire frame buffer. So it will go through every possible screen tile for every triangle and copy back and forth, which is a lot slower than it needs to be. But that's just me doing the naive thing first. So since a lot of these triangles are very small, this could be a lot faster just by not doing those copies. But again, those copies themselves, those have to go over UART right now. And that's very slow because the UART connection I have is like 400 kbaud or something. So that's like 40 kilobytes a second or something. But you guys, this works. This is so sick. I'm gonna post the tiniest little screenshot. Actually, I'll post a screenshot from OBS because that's a bit better. I gotta smile for the camera. No, I gotta do a better one. Like really pumped. Yeah, that's perfect. This is great. I'm tweeting this. Tweeting this right now. It'll be, yo. And I'm going to send it to the Games Tech Slack because I have to. This is great, you guys. I'm so pleased. And I'm really happy I streamed this. That's great. Well, I'm just sitting here just like loving this. I'm just so happy right now. So I'm not saying much. It's just that I'm so chill now that this actually works. Like, this is so sick. And again, this totally validates the way that I'm doing this. Like the fact that I can sit there and make some isolated. Thanks, Love Like Semtex. Yeah, so happy that I could like isolate this individual hardware unit and make a test on its own, just without anything else. Verify that it's starting to work. Plug it into the system without too much fuss, and then actually get it working with some software changes. Again, this is not a full like driver for this, but I can kind of develop most of that again in sim. Yeah, that was the other thing. Like again, verify that in sim, and then it just works by the time I put it on the device. Now, I suspect as things get more complex, we might run into like timing issues and stuff. Maybe we will, maybe we won't. I mean, if I design this right, we won't, ideally, but who knows? Anyway, I'm pumped. Yeah. Yeah, I don't really have much else to say. I feel totally validated in this approach, and I'm so stoked that this is working. I might make a small change now, actually, to add a command specifically to fire off rendering and then wait for that to complete, and also count cycles. Because it would be nice to validate on the actual hardware that it takes as many cycles as I expect. But you know what? No, I don't want to do that right now. I'm just going to enjoy this. I'm going to take the win, and I'm going to enjoy it. And I might go, too. And just chill and open the fucking window because it is so hot in here. But you guys, I'm so stoked. So now what comes next is like cleaning up all this shim harness stuff and kind of ideally making something that's a bit easier to kind of plug in new modules than this, because like I totally hacked, arguably broke the main top level code that I used to test, just to get this like driver on the host. So I won't push this for a while because I need to clean everything up, but yeah, that would be the next steps. And then yeah, after that it's getting the Rasterizer to be better, like implement texture support. And I still need to go back to the software model that I have and kind of figure out some more bit widths and start actually pipelining that and everything. And also the RTL code that I wrote for the GPU needs to be done better. And I need to like unify the interface to the GPU instead of having two ports, like I have now. But anyway, long list of things to do from here. But like, I'm really happy that I went and just started working on this part now instead of waiting until I finish rasterizing the renderer, because this is extremely motivating to see. And again, very validating for the approach. So yeah, I'm pumped. I'm really pumped. I am going to go and cool off and watch TV or something and just let this run because this is really sick. So yeah, thanks guys again for hanging out. And I will definitely see you next time.